All right, so we're going to walk through the solutions to our Unit 4 review, Part A. So I have these already on the answer key for you to look at separate from the video. So we're just going to go over them, and then I'll add in the shown work for the calculation problems. So in the first couple of problems, draw the free body diagram of the underlined object in each situation. So a book is on a table. So we need to draw a free body diagram of the table. So here's a picture. The table is in contact with the book, and then the table is also in contact with the floor. So we start with a dot representing the table, and then as always, force of gravity on table by earth. And then since the book is above the table, the book is pushing the table down. It's in contact, so that's a normal force, downwards on table by book. And then since the floor is under the table, the floor is pushing the table up. Again, a contact force, so a normal force on table by floor up. Since it's at rest, the one normal force up will equal the sum of the two forces down. So that's why this one's larger. Between force of gravity and book being greater, it looks like the table's probably heavier than the books, but those are just relative. You can choose how heavy of a table versus a book that is. Okay, then scrolling down to the next one, a box slides down an incline at a constant speed. So here's the direction of the incline. So represent the box with a dot. We have force of gravity on box by earth straight down. And then I don't have drawn in here, but we could draw in our x-axis and our y-axis parallel to the incline and perpendicular to the incline. From that, draw in the y and x components of gravity if that helps you visualize it. So then going up perpendicular to the surface of the incline is normal on box by floor or incline. Since the box is sliding down the incline, kinetic friction is opposite the direction of motion. So since the box is going down, kinetic friction goes up the inclined surface. And it's kinetic friction because it's sliding. So it's only those three forces. You don't have to draw out the x and y components on the force of gravity, just if that helps you visualize it. And then saying constant speed, that just means that the normal force and the y component of gravity are congruent or equal. And then the x component of gravity and kinetic friction are also congruent or equal. Balanced forces for constant speed. Okay, next is a different one that we haven't done since the beginning of the unit. We have an airplane flying level at constant speed. So a dot to represent the airplane. We have force of gravity on plane by earth. And then keeping the airplane up is the air pushing the wings up. So it's a contact force, so we can call it normal force on plane by air. Or if you remember, there's a specific name for this force, but it's lift. So if you want to say it's the lift instead of normal force, that's totally fine. And then the airplane is moving forward because of its engines expelling fuel. So that's pushing the plane forward. So normal on plane by expelled fuel. And airplanes are aerodynamic to an extent, but there is still air resistance on plane by air. Since it's level at constant speed, the vertical forces are congruent or equal, and the horizontal forces are also congruent or equal. Okay, last one, we have a rock climber climbing up a rock wall. And I took this picture to help orient the direction of all of the forces. So a dot to represent the rock climber, force of gravity on person by earth. And then notice their feet are in contact with the wall. they're pushing themselves out. Also, when you're climbing, you want to have grippy shoes. You want your feet to not slip on the rock. So you also have friction, preferably static friction so you don't slip. And then there's also tension, and this rope is at an angle. So we have the tension on person by rope. The rope is pulling the person up. And then since the feet are flat against the surface of the rock, the wall is pushing, or the rock is pushing the person out by their feet. And then also because their feet are not slipping preferably, there's a static friction up on person by rock. Static friction and normal force are always perpendicular to each other. And when you're pushing against the rock, it pushes you out, but also you're not slipping, so it helps you go up. I'm going to go ahead and just scroll past 2 and 3, as these ones are just copy and pasted from our statements of Newton's first and third laws in our notes. Let's go on to 4. So Mitch is pulling his dog in a wagon across a grassy field. He pulls the wagon at a constant speed with a force of 35 newtons, and the angle the handle makes with the ground is 28 degrees. The total mass of the wagon and dog is 42 kilograms. First, we're going to draw a free body diagram of the wagon with the dog in it. So we're treating the dog and wagon together. So dot to represent the wagon and dog. Force of gravity on wagon by earth. And then we're told at an angle of 28 degrees, so that's the handle angle with the ground is 28 degrees. So tension on wagon by boy, or Mitch. And then, since it's in contact with the grass, there's a normal force on wagon by grass. And then there is friction on wagon by grass. And technically with wheels, it's static friction because the surfaces of the wheels are not sliding across each other, but are rolling. If you said kinetic friction, that would be okay because we haven't really talked about wheels being static friction. But think of the surface of the wheel in contact with the grass. They're not sliding against each other. So it's static friction. Okay, we finally get to some calculations. So in the answer key, you have the answer, but how do you get the answer? Well, let's set up our equation. We're looking for the normal force up on the wagon by the grass. That's this force upwards here. We have drawn in the free body diagram, the y component of tension is also up, and then we have force of gravity down. So we have force of gravity is the only force down, and that's going to equal the force of normal up plus the y component of tension up. We do not yet know the y component of tension. We'll need to calculate that. And we also need to calculate the force of gravity. So if you remember, our force of gravity equation is mass times acceleration due to gravity, which is g. That again equals the normal force, which is what we're looking for. And then for the y component of tension, since that's a horizontal angle, we're going to use sine to find that y component. So we have force of tension times sine of the angle of 28 degrees. Okay, now we can just plug in all of our numbers. So the total mass is 42. G is 9.81 because we're on Earth, assumably. We're looking for normal force. We're told that tension force is 35 newtons. And then sine of 28 degrees. You can either plug or multiply and find this first, and then rearrange, or rearrange first. Your choice. When you're in Desmos, make sure you're in degree mode. Good, still am. So let's find all of these values here. And 35 times sine 28. I'm just going to do 4 decimal places for now. Okay, then we'll subtract to the other side. So the 412 minus the 16. And that's how we got our answer of the normal force being 395.59 rounds up newtons. Okay, so we started with our vertical force equation, substituted how to calculate the ones we knew, plugged in our numbers, and solved for the missing force. Okay. Last part of this question, what is the force of friction on the wagon by the grass? So the force of friction is horizontal to the left. And then we have an x component of tension horizontal to the right. Those two are going to be equal since we're moving at constant speed. So to set up our equation, we have static friction equals the y component of tension, or sorry, the x component of tension. And we can solve for that x component of tension. Since the angle is from the horizontal, we're going to use cosine. So the total tension times cosine of the angle, which is 28. So then plugging in our value for tension, because we're told Mitch pulls with 35 newtons. So 35 times cosine of 28. On Desmos, cosine 28 times 35. And that's how we got our answer of 30.90 newtons. All right. So I'm going to pause the video here because if the video gets too long, it doesn't like to upload. So watch video part 2 to see the next problem.